Today's notes are about motion diagrams again. We're just elaborating on what the last video actually was mentioning. In the last video we looked at particle diagrams, so representing an object moving as dots in a direction. We're going to add to that by adding a coordinate system. A coordinate system is just used to help explain the motion and represent scale. It tells us how far an object moves or in what time period how much it moves. So it helps us describe motion better than faster, slower, speeding up, slowing down, things like that. All coordinate systems must have an origin. An origin is simply the starting point. The way an origin works is it tells us whether our motion is positive or negative. So here we have Mr. Mohawk Man, and we have two different origins. We have him starting at 0 point on this coordinate system, and him starting at -35. Both systems are equally correct. The only difference between them is where the origin is. This one's origin is 0 where he's at. The origin on this one is 0 at the finish line. Once we have our origin, we can actually describe our motion as positive or negative. So since he's running from left to right on this page, he would have a positive motion, since he's moving to the right of the 0 point, or towards the right of the 0 point. If he was starting on the right-hand side of the paper and moving to the left, then we could say that he has negative motion. We can also describe motion relative to a reference point. Keep in mind that a reference point is just relative. It's just any object that we can use to describe or measure the motion. We usually have reference points that don't move because we're comparing one thing to another. So you could be on a train, and relative to the ground would be your reference point, the train and you are moving. Or your reference point could be another passenger on the train. So if you get up and walk back and forth on the train, according to that passenger, you're moving. But the train is not. So reference points and relativity all kind of change. We usually try to keep things that don't move, though. Another way of describing our motion is by use of position vector. Position vector just shows the distance and direction from the reference point that a person is moving, or in the event of a coordinate system, from the 0 point. Keep in mind that this is a position vector. A vector must have magnitude and direction. If it only has magnitude, then it's a scalar quantity. So 55 miles per hour would be a scalar quantity, whereas 55 miles per hour east would be a vector. Vector has magnitude and direction. Scalar is only magnitude. Along with vector quantities, arrows of equal length, we'll be using these a lot when we're looking at forces and displacements. Arrows that are the same length represent the same magnitude. So these two vectors represent 5 meters or 5 newtons force. Keep that they're the same length. This one is 3 times the length of either one of those, so then it is 15. So the relative size of a vector indicates its magnitude. The whole reason why we're looking at motion and displacement and vector quantities and scalar quantities because we can actually use those to represent a full motion diagram. We've been working with particle diagrams, but they don't really tell us a lot other than what operational definition the object is experiencing. By adding the displacement and time, we can pick up a lot more information from what's going on. So down here I have a motion diagram and a particle diagram drawn for this situation. So we have a guy named Ted walking 10 meters in 15 seconds, jogging 25 meters in 20 seconds, and then sprinting 30 meters in 12.5 seconds. So I've represented the particle diagram. We can see here the spacing is fairly close because he's not moving very fast. Between this segment and this segment, he's moving more, so the dots get further apart. And then between this segment and this segment, he's moving much faster, so the dots are further apart. That's just our particle diagram. Now, to make this a motion diagram, we add displacement and time. So displacement here I have represented by a D. You can see that here's our origin, D0. For the first segment, he moved 10 meters, so between the next point, we can see that D is now 10 instead of 0. Moved 25 during the next segment, so instead of 10, it is 35, because we have to add the 25 to the 10. This is distance from the origin. If we wanted to find just the distance of this segment, we would have to take 35 minus 10. And then for our last segment, he moved 30 meters, so we'd take 35 plus 30, so that would tell us that this point is 60 meters from the origin. Since the time, in this case, we can't have the same scalar value as we did with distance, we just represent time below. So time 0, time 15, time 35, and time 47.5. These points are connected. So distance 35 and time 35 are connected because they both represent something that's happening at that time and that distance. So distance is what we used as our scale. Each time is connected to each of those distance points.